you think of a function, you likely imagine some rule that takes a real number from a set called the domain and maps it to another real number in another set called the range. Here, we expand this idea of a function to include rules that take vectors of real numbers as their inputs. Specifically, we'll look at cases where the function sends a vector in its domain to a real number in its range. This case, alongside your more, let's say, traditional case, comprises a category of functions we call real-valued functions. We call them real-valued functions because their ranges are sets of real numbers. We'll also be interested in the case where a function takes a vector in its domain and maps it to another, possibly different vector in its range. This kind of function is called a vector-valued function, again in recognition of the kind of object found in its range. We're not going to have an exhaustive conversation about real-valued functions of vectors. Instead, we're going to focus on linear ones. We'll define a linear, real-valued function of a vector, let's call it little f, as one that takes its input x and maps it to the new expression shown here. Here, each of a1, a2, etc. is a constant that is given. Here's an example of a linear real-valued function that takes the vector x and maps it to the real number negative 2x1 plus 3x2. In this example, the constant a1 from our definition a moment ago corresponds to the number negative 2, and the constant a2 corresponds to the number 3. Like other linear real-valued functions, the function in this example can be seen to preserve linear combinations of vectors. In other words, combinations of vectors like c1x plus c2y, where c1 and c2 are constants. To see what I mean when I say f preserves linear combinations of vectors, consider running the linear combination c1x plus c2y through the function f. Doing so gives us the following. Next, distributing negative 2 and 3 respectively over the terms you see in brackets gives us this, which simplifies to this, and ultimately to this. Basically, we see that the function preserves linear combinations because applying it to any such combination, like we did here, is the same as taking the linear combination of the function applied to x and y individually, as shown here. Importantly, nonlinear functions do not preserve linear combinations of their arguments. One final note about linear real-valued functions is that they can be written as a dot product when the coefficients a1 to an are themselves stored in a vector. With this in mind, the function we encountered in the last example could have been expressed as the dot product of the vector negative 2, 3 with the vector x. Recognizing that linear real-valued functions can be expressed using a dot product is helpful if you want an alternative way of convincing yourself that these functions do indeed preserve linear combinations of vectors. In fact, you can demonstrate preservation of linear combinations simply by applying what you know about the distributive property of dot products and how dot products work with multiplication by a constant. Let's shift gears now and talk about linear vector-valued functions with vector inputs. This category of function takes an n-dimensional vector x and maps it to an m-dimensional vector called capital F of x of the form shown here. Note that a1 through am are given n-dimensional vectors. Note also that each element of capital F of x is itself a linear real-valued function of the vector x. It follows that the linear vector-valued function capital F inherits preservation of linear combinations of vectors from the real-valued functions that make it up. We're really interested in the case where the vector-valued function capital F of x and the vector x itself have the same number of elements. As an example, consider capital F of x defined as the vector whose first element is negative 2x1 plus 3x2, and whose second element is x1 plus x2. Here, the input vector has two elements, x1 and x2, and so too does the vector output by the function. We have a special name for this kind of vector-valued function. We call it a vector field. The name here might make better sense if I tell you about one way we can visualize vector fields graphically. Essentially, we create a plot in n-dimensional space by applying the vector capital F of x, pictured as an arrow, to the vector x, pictured as a point. So, if we wanted to visualize the example shown here, we would draw two-dimensional space, find some point, say the vector 1, 2, and apply capital F at this point. To be clear, when applying capital F at the point 1, 2, or the vector 1, 2, we move over 4 and up 3 because these are the elements of the vector output by our vector-valued function. If we repeat this procedure a number of times at many different points in the plane, then we get a plot that looks like this. A field of vectors. A field of vectors that suggests movement or flow. Given that the plot suggests movement, it's hardly surprising to find out that vector fields play an important role in models of dynamic biological phenomena. More about that in later videos. For now, let's recap. In this video, we learned about two categories of function that take vectors as input: linear real-valued functions and linear vector-valued functions. Both preserve linear combinations of inputs. We saw that linear real-valued functions can be expressed using dot products of vectors. And we discovered that certain linear vector-valued functions, namely vector fields, can be visualized in a way that suggests motion in multidimensional space. By the time you've mastered the ideas presented in this video, you should be able to do three things. First, you should be able to define and identify linear real-valued functions, linear vector-valued functions, and vector fields. Next, you should be able to show that a linear real-valued function preserves linear combinations of vector inputs, and you should be able to do the same for linear vector-valued functions. Finally, you should be able to construct a graphical representation of a linear vector field, one that conveys a sense of motion. Remember, success in math is not built on only watching videos. Read the notes, try the problems, make up problems of your own and share them with a friend. Turn the ideas over in your head in different ways and you'll get it in no time.